Ladies and gentlemen, please give a warm welcome to the laureates of the 2018 Tang Prize in Sustainable Development, Dr. James Henson, Dr. Veerabhadran Ramanathan, and our host, Dr. Chao Han Liu. Good afternoon, distinguished guests, ladies and gentlemen. Welcome to the Laureate Lecture of the 2018 Tang Prize in Sustainable Development. To begin with, we would like to invite to the stage the host of this lecture, Dr. Chao Han Liu, academician of Academia Sinica, to give us the introduction. Ladies and gentlemen, please give a warm welcome to Dr. Liu.
Good afternoon, ladies and gentlemen. It's my honor, my pleasure to introduce to you two master lecturers for this afternoon on the Sustainable Development category of the Tang Prize of 2018. Let me first say a few words about this particular category. As many of you probably know, the Earth, our planet, is now into the so-called Anthropocene, which is a period of geological period in which human activities have been the dominant influence on the condition of the planet. Science and technology actually have been the main driver behind this influence. And as we all know, they have brought many much needed and timely benefits to human society over the years, over the ages, helping us shape our civilization. But they also led the human society to a path where we now have to face an existential problem. That problem is, can human beings, human society, as we know it, be sustained? Human beings have brought ourselves into an abyss. Can we find ways to avoid the Armageddon? The Tang Prize for Sustainable Development is designed to help us to answer this question. The prize is awarded to those who have made extraordinary contributions to the sustainable development of human societies, especially through groundbreaking innovations in science and technology. And the prize is, as we all know, quite multifaceted. It includes areas such as energy, climate, biodiversity, engineering, as well as science policies related to sustainable development problems. In particular, the prize is awarded to persons who have made similar contributions to the science itself, as well as they have applied the knowledge to try to solve the problems, the sustainability problems. This year, the prize was awarded to 2 climate scientists who fit perfectly into this description. Dr. James E. Henson and Professor Ramanathan. Dr. Henson was awarded for sounding the alarms, on climate change, elucidating the physics of climate forcings and feedbacks, and quantifying the dangers of global warming and tirelessly advocating meaningful action and solutions. Professor Ramanathan is awarded for making similar contributions to our fundamental understanding of climate change and impact of air pollution, and taking direct action to advocate and facilitate effective mitigation solutions, policies. And now, the 2 laureates today will give us the master lectures. First one is Professor Tmc Henson. I'll briefly introduce him to the audience. Dr. Henson was born in Iowa, United States. He studied at University of Iowa and received his PhD in the university under Professor Van Allen in 1967. He worked at NASA's Goddard Institute for Space Studies, GISS, for more than 30 years. And he has been at the forefront of advocating scientific understanding, advancing scientific understanding of the climate change phenomena. He was the first to detect the greenhouse warming signal on the Earth, and he was the first to warn the world of the danger of the intensive storms and extreme weather events in the future. And his advocacy of action to avoid dangerous climate change has inspired many people, especially young people around the world, to join the fight to mitigate the climate disaster in the world. Today, he will talk to us about global change, global energy, climate and health, young people's burden and opportunities. Ladies and gentlemen, please join me to welcome Dr. Henson.
Thank you. I'm glad to see some young people in the audience. This is really all about you and the planet that we're leaving for you. Energy enriches our lives. 1 liter of petrol contains the work equivalent of 100 hours of labor by a healthy adult. Fossil fuels powered the Industrial Revolution, raised living standards, and helped eliminate poverty. Fossil fuels also affect the climate and human health, leaving young people burdens that must be turned into opportunities. That requires an understanding of science and technology. Let's start with the climate story. So what do I know that would cause me, a soft-spoken Midwestern scientist, to get arrested protesting in front of the White House? I was lucky to grow up at a time when it was not difficult for the child of a tenant farmer to make his way to a state university. And I was especially lucky to study under Professor James Van Allen, who built instruments for the first United States satellites at the University of Iowa. Professor Van Allen told me about observations of Venus. Venus was emitting intense microwave radiation. Did it mean that Venus had an ionosphere, or was Venus extremely hot? The right answer, confirmed by Soviet Venera spacecraft, was that the surface was very hot, 900 degrees Fahrenheit, kept hot by a thick carbon dioxide atmosphere. Mars, Earth, and Venus confirm the greenhouse effect. The greenhouse effect is the excess temperature relative to what is expected given the amount of sunlight each planet absorbs. And as the greenhouse gas amount increases, excess warming increases. Earth is not too cold or too hot. It's just right for life. I was fortunate to join NASA and successfully propose an experiment to fly to Venus. Our instrument, which is a telescope 1.5 inches in diameter, took this image of the veil of Venus, which turned out to be a thick smog of sulfuric acid. While our instrument was being built, I became involved in calculations of the greenhouse effect here on Earth because we realized that our atmospheric composition was changing. So I resigned as the principal investigator on our Venus experiment because changes on our own planet are more interesting and important. They will affect all humanity. The greenhouse effect had been understood for a century. Irish physicist John Tyndall in the 1850s made laboratory measurements of infrared radiation, which is heat. And he showed that gases such as CO2 absorb heat, thus acting like a blanket, warming Earth's surface. I worked several years on climate observations and building a climate model with colleagues. In 1981, we published an article in Science magazine concluding that Earth had warmed 0.4 degrees Celsius in the prior 100 years, that observed warming matched our calculated warming due to increasing CO2, that Earth would warm more in the 1980s, and that warming would exceed natural variability before the end of the century. We also said that the 21st century would see shifting climate zones, creation of drought-prone regions in North America and Asia, erosion of ice sheets, rising sea levels, and opening of the fabled Northwest Passage. All of these have since occurred. That paper was reported on the front page of the New York Times and led to me testifying to Congress in the 1980s. Testimony in which I emphasized that global warming increases both extremes of the hydrologic cycle. Heat waves and droughts on one hand, directly from the warming, but also because a warmer atmosphere holds more water vapor with its latent energy, rainfall can occur in more extreme events. There are stronger storms and greater flooding. After I complained that the White House had altered my testimony, global warming hoopla became time-consuming and distracted me from doing science. So I decided to go back to strictly doing science and leave the communication to scientists who were good at media communication and even enjoyed it. By 15 years later, evidence of global warming was much stronger. Most of the things mentioned in our 1981 paper were established facts. I was privileged to speak twice to the President's Energy Task Force, Vice President Cheney, and 6 cabinet members. But U.S. energy policy continued to focus on fossil fuels. At the same time, my view of the safe level of atmospheric CO2 began to diverge sharply from that of prominent climate science communicators. And by then, I had 2 grandchildren. I decided that I did not want them in the future to say, Opa understood what was happening, but he didn't make it clear. So I decided to make a public statement criticizing the lack of an appropriate energy policy. After I encountered resistance to giving the talk in Washington, Professor Van Allen kindly arranged for a lecture at the University of Iowa in October of 2004. And 14 months later, I gave a similar talk at the 2005 American Geophysical Union meeting. That talk led to several calls from the White House to NASA headquarters. And I was told that I could not give any more talks or speak with the media without explicit prior approval by NASA headquarters. After I informed the New York Times about these restrictions, NASA was forced to end the censorship. But there were consequences. I had used the first line of the NASA mission statement to understand and protect the home planet, to justify my talks. Soon, this line of the mission statement was deleted, never to appear again. In the next few years, I was drawn more and more into communicating the urgency to change energy policies, while still researching the physics of climate change. Let me describe 2 of the most important pieces of that physics. Adding CO2 to the air is like throwing another blanket on the bed. It reduces Earth's heat radiation to space. So there is an energy imbalance, more energy coming in than going out, until Earth warms up enough to again radiate to space as much energy as it absorbs from the sun. Earth's energy imbalance is the key quantity. If more energy is coming in than going out, then more global warming is in the pipeline, and it will occur even without any more greenhouse gases. We can now measure Earth's energy imbalance by measuring the heat content in Earth's heat reservoirs. The biggest reservoir, the ocean, was the least well measured until more than 3,000 Argo floats were distributed around the world's oceans. These floats reveal the upper ocean is gaining heat at a substantial rate, and the deep ocean at a smaller rate. Energy is also going into net melting of ice around the planet, and the continents to depths of tens of meters are getting warmer. The total energy imbalance is now about 3/4 of a watt per meter squared. That's about 20 times greater than the rate of energy use by all of humanity. It's equivalent to exploding about 500,000 Hiroshima atomic bombs per day, 365 days per year. That's how much extra energy Earth is gaining each day. This imbalance means there is more warming in the pipeline without additional CO2. It also means if we want to stabilize today's climate, we must reduce CO2 from 410 parts per million to at most 350 ppm. That's the change needed to restore energy balance. Climate change deniers argue that the sun is the main cause of climate change. But the measured energy imbalance occurred during the deepest solar minimum in the record, when solar energy reaching Earth was least, yet more energy was coming in than going out. So the effect of sun's variability is overwhelmed by the increasing greenhouse effect due to fossil fuel burning. Earth's history contains remarkable information on climate change. Global temperature, atmospheric CO2, and sea level over 800,000 years can be derived from ocean cores and Antarctic ice cores, from ocean sediments and from the snowflakes that pile up year after year and form a 3-kilometer thick ice sheet. Sea level is a measure of ice sheet size. When the ice sheets melt, sea level rises. Climate change on such long time scales is instigated by oscillations of Earth's orbit and the tilt of the Earth's spin axis, which alter the seasonal and geographical distribution of sunlight on Earth. These orbital forcings are weak and slow, changing on time scales from 20,000 to 100,000 years. Climate changes on these long time scales are very large. The large magnitude is due almost entirely to two powerful amplifying feedbacks, ice sheets and CO2. As Earth warms, ice melts and exposes darker ground that absorbs more sunlight. As the ocean warms, it releases CO2 like a warm Pepsi. CO2 changes more slowly than ice sheets, so it is the control knob on global temperature. As you can see from this remarkable comparison of atmospheric CO2 and Antarctic temperature. The same amplifying feedbacks must occur today. Physics does not change. As Earth warms, ice sheets will melt. CO2 and its companions, methane and nitrous oxide, will be released by warming ocean, melting tundra, and wetlands. We can't say exactly how fast these amplifying feedbacks will occur, but they will occur. Now let's tack modern data onto the paleo record. CO2 is shooting off scale. Temperature is also rising, but it has not caught up to the CO2. That takes time. Why? First, the ocean has great thermal inertia. It takes 100 years for the ocean surface temperature to reach 2/3 of its equilibrium response. Second, there are slow feedbacks. Ice sheets do not melt overnight. The paleoclimate record shows sea level lagging temperature by a few centuries. So does that mean that coastal cities are safe for several centuries? No, because human-caused change in greenhouse gases is much faster than any change in Earth's history. In our paper, Ice Melt, Sea Level Rise, and Superstorms, we estimate that multimeter sea level rise can occur in 50 to 150 years if CO2 continues to increase rapidly. Sea level rise does not need to reach several meters before the economic impact becomes intolerable and the world likely becomes ungovernable. Cities become dysfunctional long before they are totally underwater. These are all the world's largest cities. As you can see, more than half of them are on coastlines. Florida, the Netherlands, and Bangladesh would be underwater, and a good part of China. The second irreversible impact of rapid, large climate change would be on other species. We cause stress on other species in many ways as we take over the planet. We could commit to extinction 1/4 to 1/2 of all species from the combined effect of these stresses and rapidly shifting climate zones, according to estimates of the Intergovernmental Panel on Climate Change. Coral reefs are the rainforest of the ocean, harboring more than 1 million species. They are threatened by many stresses, including ocean warming, which causes coral bleaching, and ocean acidification, which in the extreme can dissolve the carbonate exoskeletons. We are losing more than 1% of the coral each year. If rapid emissions continue, especially with rapid sea level rise, most coral could be lost. However, if we reduce CO2 emissions to stabilize shorelines, we will also solve this problem. Older people notice that climate is already changing, especially in the summer. Year-to-year variability of seasonal temperature in the 20th century formed a nice bell curve about the average. But now that bell curve has shifted. What was an unusual extreme hot season last century is now much more likely to occur. The change depends on location. In middle latitudes, in the US and Europe, the shift is a bit more than 1 standard deviation in summer, but smaller in winter. In the subtropics, such as the Mediterranean and Middle East and Southwest United States, every summer is now hotter than average climate 50 years ago. And that's almost true in Southeast Asia today. Increased heat causes dry regions to have more drought and wildfires and a longer fire season. But warm air holds more water vapor, so wet regions and rainy seasons can have more extreme rain and floods. Low latitudes are becoming less livable outdoors in the warm season. And more than half of the jobs are outdoors in agriculture or construction. Higher temperatures also lead to a measurable increase in violence. These things are happening. Dry regions are having more extreme events. Here are fires in Greece this year. These are more images from the fires in Greece. Fires have always occurred, but despite massive efforts to extinguish fires in the U.S., the area burned is increasing. 100-year floods are now occurring more than once a century. There was unprecedented rainfall amounts in Japan this year. A warmer ocean surface and more water vapor in a warmer atmosphere provide more fuel for stronger tropical storms, tornadoes, and thunderstorms. This super typhoon had the strongest sustained winds over land ever recorded, reaching 195 miles per hour, which is well over 300 kilometers per hour. Yet the urgency of the climate crisis is not recognized by most people, by most of the public. Because of the ocean's thermal inertia, much of the warming is still in the pipeline, and that warming will drive slow feedback, such as melting of permafrost and ice sheets. So, if the world does not reduce fossil fuel emissions, it will be an injustice to young people, because we will hand them a situation out of their control. It also would be an injustice of the industrial North, which is burning the allowable carbon budget for the entire world. And, of course, an injustice of humans to all other species. Okay, now you know why I got arrested. After I was arrested 5 times, I finally realized, hey, this is not working. Drawing attention to the injustice of climate change does not alter government policies. Energy use continues to grow. People want to raise living standards. People want to travel, and they will. They need air conditioning. The world needs energy. Governments give large subsidies to renewable energies and pretend this will cause fossil fuel use to decline. As you can see, the fossil fuel use continues to increase. Courage to use the true scientific method is lacking. So governments continue to seek fossil fuels, and there are plenty to find. We have burned only the purple portion so far. The science is crystal clear. We must leave most of the remaining carbon in the ground. And we must extract some CO2 from the air, which is possible via improved agricultural and forestry practices. However, we must leave young people a feasible task and tools to address it. Young people must take up the fight, and they must demand their rights. But to succeed, they must understand the matter and use the scientific method. We old scientists failed to change the world's course. I hope to explain to young people what I learned in Sophie's Planet, a book that I'm writing. And thanks to the Tang Prize, I should be able to finish that book very soon. The core of the scientific method is simple in principle. You must use all the data, be very skeptical of your interpretation, and honestly reassess from scratch when new data becomes available. Your preference, your ideology must not affect your assessment. So it is difficult. Now let's consider human health as another huge issue associated with energy. China did an inadvertent experiment by providing free coal for winter heating to people in North China for several decades. It reduced their life expectancy by 5.5 years. Globally, outdoor air pollution, mainly from fossil fuel burning, is killing more than 3.5 million people per year. That's 10,000 people per day. The aerosols that people breathe are so tiny that they enter the bloodstream, causing cardiac problems as well as respiratory problems. Indoor air pollution from burning coal, wood, and other biofuels kills an additional 3.7 million people per year. And because these fuels are used for cooking, women and children are especially affected. Many of the deaths from air pollution are prolonged and painful to the victim and the family. The crucial requirement to solve both health and climate problems is abundant, clean, carbon-free energy. However, fossil fuels will not be replaced by an alternative unless the entire energy system is economic relative to coal and gas, including costs of additional transmission lines and energy storage if those are necessary. India will soon pass China in population, and India will pass the US in carbon emissions, becoming second to China. Renewable energy, the green area, provides only a tiny portion of the energy. It cannot stop growth of fossil fuels, let alone cause their phase out. Energy history of the United States is educational. Wood was the first energy source, but coal with greater energy density powered the Industrial Revolution until the more convenient liquid and gas fossil fuels were discovered. Because fossil fuels are a finite resource and a big pollution problem, it was hoped that peaceful use of nuclear power would be a major long-term energy source. There is enough nuclear fuel in the ocean to last forever, for billions of years. So it would be possible to stop mining of uranium or thorium. Nuclear power could potentially eliminate CO2 emissions as well as air and water pollution. However, development of nuclear power practically stopped in the 1970s. What happened? The root problem for nuclear power is concern about health effects of atomic radiation. Until 1956, it was assumed that there was a threshold for harm, consistent with the idea that radiation is probably not dangerous if it is less than the amount that we get from cosmic rays and radioactive elements in the soil. Some scientists even argue for radiation hormesis, the idea that low levels of radiation are beneficial. However, in 1956, the National Academy of Science Baer Committee, Biological Effects of Atomic Radiation, declared that the tiniest amount of radiation is harmful. Linus Pauling used the idea that even the tiniest radiation is harmful to help achieve a ban on atmospheric testing of nuclear weapons by the US and USSR. This, incidentally, had an effect on public perception of nuclear power. Public attitudes were also affected by the 1979 disaster thriller, The China Syndrome, about the danger of a nuclear meltdown. The film almost coincided with an actual accident and partial core meltdown at the 3 Mile Island power plant in Pennsylvania. Enthusiasm for nuclear power in the U.S. dissipated, even though it was determined later that the radiation released did not harm Pennsylvania residents. This is from a concert held that year in New York.
The energy that we have now, we have to have either oil or coal or whatever, but certainly not nuclear. Even wood if need be. I have a coal stove at home if you want to know. Flash! Yes. Put it on. I don't use it now, but if I have to, I will. And I live 1 block from the mayor, and I have a coal stove. Put that in your house and smoke it.
Song of our movement. Just give me the warm power of the sun. Give me the steady flow of the waterfall. Give me the spirit of living things as they return to clay. Just give me the restless power of the wind. Give me the comforting glow of the wood fire. But please take all your atomic poison power away. Take all your atomic poison power. Take all your atomic poison power away.
So did you hear the line in the song, "Give me the warm glow of a wood fire"? Remember that 10,000 people per day are dying from indoor air pollution. Proponents of nuclear power continue to argue that the Baer Committee was wrong, that LNT is not correct and was ideologically driven. I doubt that this battle will be fruitful. Small radiation effects are difficult to prove and depend on the circumstances. In such case, health professionals are likely to prefer the strictest criterion, which is LNT. However, young people have a good basis to be very unhappy with us old people for not being scientific, for not being objective. We owe it to young people to provide an honest comparison of the health and environmental effects of nuclear power, health and environmental effects of fossil fuels, and health and environmental effects of renewable energies. We have science academies capable of such evaluations, which should be presented side by side. Young people have more reason to question the wisdom of us old people. President Clinton, 25 years ago, terminated R&D on nuclear power, just when the Department of Energy was ready to build an advanced generation nuclear reactor with major improvements over today's reactors, which are 50-year-old technology. Nuclear power in the U.S. has an outstanding safety record, but next-generation nuclear power can be even much safer and produce less nuclear waste. We would not force solar energy or windmills to use 50-year-old technology. I am not advocating any specific technology. My opinion is that because of prior government failure to support R&D, the best chance now for advanced technology to contribute to rapid phase-down of CO2 emissions in the near term is probably via modular light water reactors. However, the Nuclear Regulatory Commission and the Department of Energy need to facilitate progress with modern technology, which they are not doing well. Canada has a more responsive regulatory commission. Yet from an engineering perspective, the best nuclear innovation potential still seems to be in the U.S. So let me give the last word on this topic to my oldest grandson. Here he's at about age 7, reading an Indiana Jones book about an urgent problem. A few years later, Connor correctly identified 2 basic conclusions about the energy climate matter. First, if grown-ups keep doing what they're doing and kids can't figure out a time machine that actually works, then kids are screwed. Second, some grown-ups are scared of nuclear power, but what about fossil fuels? We know that using fossil fuels is not safe. It is very dangerous. Now, let's consider the solution to the health and climate problems. The essential requirement is a rising carbon fee to make the price of fossil fuels honest by including their human health and climate change costs. It's easy to implement an across-the-board carbon fee, collecting it at the first sale at domestic mines and ports of entry. If 100% of this collected fee is distributed equally to all legal residents, we obtain a simple, transparent, market-based approach that spurs innovation. With the present distribution of energy use, 70% of the public will make money. But if they want to stay on the positive side of the ledger, they need to pay attention to the price of things on the shelf. Products that employ a lot of fossil fuel in their production will become more expensive. Most rich people have a large carbon footprint from large houses and flying around the world, so they will lose money, but they can afford it. Fee and dividend spurs the economy, creating jobs, increasing GNP, and increasing government revenue. Fee and dividend is the one effective international approach. When the US and/or China adopt a carbon fee, they will also impose border duties on products from countries that do not have an equivalent carbon fee. That will be an incentive for other countries to adopt a carbon fee so they can collect the money themselves. So the crucial underlying requirement is a rising price on carbon to make the fossil fuel price honest. Some regulations will still be required, and governments should support research and development because it is essential to have 100% carbon-free electricity. It's important to recognize national responsibilities for climate change, which is proportional to cumulative emissions. The US, the UK, and Germany are much more responsible for climate change than the developing countries. In other words, the West burned much more than its fair share of the global carbon budget that is permitted if we are to stabilize climate and avert disasters. This is an added reason for the West to assist in reducing emissions in developing countries, in addition to the fact that we're all in the same boat together. How can we reduce emissions from the big future emitters? If I want to be popular, if I want to find research support easily, I must say that renewable energies can provide all of our energy. If I want to be a good scientist, I must look at the data. Does it make sense to place all of our eggs in one basket, to make the assumption that renewable energies by themselves will rapidly replace fossil fuels? Young people should be angry. Old people do not have the right to gamble the future of young people on that assumption. I doubt that the climate problem will be solved by 190 nations sitting around a table. What is required, I believe, is the United States and China to agree on the need for a carbon fee. They could readily impose it on a near global basis. However, this will not happen in the absence of technological advances that allow practical economical movement to carbon-free electricity in countries such as China and India. For that to happen rapidly requires concerted, high-priority technology cooperation. The notion that humanity can escape to Mars is nonsense. Either we learn to work together, preserving our remarkable home planet, or we sink to the abyss together. China and India are not the only big emitters. There's also the United States, which has withdrawn from the Paris Agreement and says that climate change is a hoax. Nevertheless, there is a basis for optimism. The United States is still a nation of laws. 21 young people, including my oldest grandchild, and I have filed a lawsuit against the federal government demanding a national plan to phase down emissions rapidly. I expect that we will win this case, even with the conservative Supreme Court, because our case is based on the most fundamental constitutional principles. Young people are being deprived of life, liberty, and property without due process of law, and they are not receiving equal protection of the law. It is analogous to the case of civil rights in the 20th century. But the courts cannot write laws, so it is important to also influence the legislative branch. Good progress is being made in the U.S. by a rapidly growing organization, Citizens Climate Lobby, which has carbon fee and dividend as its objective. CCL uses the democratic process. It visits Washington, speaking to congresspeople and their staffers about fee and dividend. They also write op-eds and letters to the editor. Joining this organization is probably the single most important thing a citizen can do to address climate change. There are CCL branches in India, but not in China or Taiwan, so that's something to think about. Thank you.
Thank you. Thank you very much, Dr. Henson, for this very inspiring talk. Our next talk will be given by Professor Ramanathan. I'll give a brief introduction. Professor Ramanathan was born in India and educated in India and did his graduate study in the United States. He received his PhD in 1974 from Stony Brook, the State University of New York. He, in his career, he made similar contributions in our understanding of how non-CO2 greenhouse gases, such as CFC, as well as aerosols, such as atmospheric black carbon, and how these affect climate change. He also helped to create, under United Nations, UNEP, the Climate and Clean Air Coalition to reduce short-lived climate pollutants. He started also a project called Project Surya to mitigate soot emission from solid biomass cooking in South Asia as well as in Africa. In him, we see another scientist in action indeed. Professor Ramanathan.
Thank you so much for the kind introduction. Again, it's really a great honor for me. Dr. Henson talked about extreme weather, so I'm going to pick up that theme. The science of weather extremes and its relations to climate change has improved so tremendously just in the last 5 years. The normally cautious American Meteorological Society came with a statement last November. We are experiencing new extremes because we have made a new climate. If there was any doubt, we should all be certain that the climate we are living in is new. It's not the climate we inherited. And because of the focus on the weather extremes and its linkage with climate change, there is a new science of health impacts of these extremes. And this was done by WHO and Lancet. So we teamed up at the Pontifical Academy of Science. Professor Lee was also involved in this, just last November. And this was medical experts, scientists, economists, etc. And we came with the statement that with unchecked climate change and air pollution, the very fabric of life on Earth, including that of humans, is at grave risk. This statement was subsequently signed by Stephen Hawking, who passed away, as you know. He sent me a personal note saying that he will do what he can to help issue of climate change. Of course, I've got Governor Jerry Brown, several Nobel laureates, and 14+ mayors. So clearly, now that we all agree the weather extremes are linked to climate change, we have to have an intense focus on the climate impact, the health impacts. So we then published this in Foreign Affairs. This is a journal read by most policymakers and diplomats. So we said the evidence is mounting that climate change will have an extreme impact on human health in the near future. I'm going to help define what that near future is. And there was a statement, we can have widespread impacts on mental health. So I was trained as an atmospheric physics. What am I doing talking about health effects and mental effects, right? So I need to take you through that journey, how I came to this situation. So my journey started in this village in South India. This is just next to my grandfather's house, where I spent a lot of my summers. His house was washed away. So I took this picture in 2004. The only place to sit is not inside the house, it's hot, and not outside, it's hotter. The only place is the veranda. I have sat on that veranda summer after summer, blissfully happy like these kids. So why did that topless kid come to the US? This was my single-minded dream, to buy a Chevy Impala and travel around the US. I was just 24, what do I know? But what happened to my Impala dream? I landed in the hands of Pope Francis. So how did that happen? That affiliation with the church just changed my life. I said, I cannot just do the science, I have to look at the solutions. So I'm going to do a deep dive into the science and then do another deep dive into the solutions part. Dr. Henson already introduced this. So the planet, just a cartoon, basic energy source is sunlight. Not all of that sunlight goes into the absorbed by the planet. It's reflected back to space by clouds, houses, streets, oceans, everything. So that 70% heats the surface of the planet. Then it gives off that energy as heat radiation or infrared, okay, till 70% goes out. But what does the intervening atmosphere do? The atmosphere, mainly gases, water vapor and CO2, acts like a blanket, just like a blanket on a cold winter night, traps your body heat and keeps you warmer. It traps the infrared, and so makes it harder for the energy to escape. So the ground has to get a lot more hotter to get rid of that 70%. So, I did my PhD on the greenhouse effect of carbon dioxide in Mars and Venus. Both are, mainly CO2 atmospheres. So my first thing when I jumped, I was at NASA then as a postdoc, and I was so lucky. At that time, NASA was about getting ready to launch, thinking of a climate satellite. So I joined that team. My first interest was, I want to measure the thickness of that blanket, okay? So we had in the satellite infrared radiometers, scanning infrared radiometers, so we can look through clouds or in between clouds. We measured the incident sunlight. It's a first calibrated measurement of the solar irradiance. All the energy budget components were measured. So how did I determine the thickness of the greenhouse blanket? Let me see if I can show the light here. Yeah. So we would take the scanning radiometer, look at sky in between the clouds, and measure the radiation coming through the atmosphere in the clear skies. After 2 years of averaging, that was the energy escaping to space. So then the question is, how much was the surface radiating? We had measurements of surface temperatures, both in situ and satellite measurements. So we found that the surface was radiating close to 400. By the way, the units watts per square meter is watts, the same as the energy, like you say, 60-watt light bulb, square meter to square meter of the Earth's surface. So the difference between the two gave us the direct thickness of background water vapor and CO2 and others. Now we can compare that, how our activities have thickened that blanket. So that's the way I see it. We have made that blanket thicker. And the United Nations report says, as of 2010, that blanket has become thicker by 3 watts per meter squared. So we have basically increased the thickness of the blanket by about 2%. And Dr. Henson already beautifully described what that energy means in terms of nuclear bomb. So what's contributing to that thickness? What human activities? So as of 2010, this is how many tons of CO2 we have emitted. 2 trillion tons. That's 2,000 billion tons. About 46% is still up there. About 930 billion tons in this thin shell. Just imagine the weight of that. That's equivalent to 450 billion cars circling the planet, okay? And then, of course, we are emitting about 38 billion tons every year. So this was our understanding as of 1975, CO2 was the main greenhouse gas. That's when I was a postdoc. My knowledge was of Mars and Venus. I had not that much understanding of the literature. And that year, 1974, when I became a postdoc, is when Roland and Molina, who got the Nobel Prize for this, came with the suggestion, chlorofluorocarbons, these were called freons, CF11 and CF12, were destroying the ozone layer. That was a year before. And I started looking into the greenhouse effect of this CFCs for reasons I can't get into now. And what I found were these were really super greenhouse gases, CF11 and 12. So what do I mean by that? So I need to take you a little bit into the infrared physics, why they're so potent. The potency of them is such that a ton of the CFC11 and CFC12 had the same greenhouse effect as 10,000 tons of CO2. Why is that? So now let's peel this layer a little bit more. Remember I said the blanket thickness? That's all in the infrared. So I'm showing as a function of wavelength in the infrared. That is how, this was the data collected right over the Pacific Ocean. That is what the ocean was radiating to ventilate its heat to space. What was measured was these wiggly guys. So the black shaded layer is the thickness of the blanket. Okay, you can see that is where carbon dioxide is trapping the planet's heat. And these being water vapor. Why is CO2 just here and not here? It's due to the quantum mechanics of carbon dioxide molecule. And the planet was nearly transparent in these wavelengths, 8 to 12. You see how thin the blanket is? That's the only wavelength the planet has to ventilate its heat to space. And miraculously, the quantum mechanics of CFC was such that they were absorbing in this window. They're just shutting off in that where the heat could escape. So that's one of 3 or 4 reasons why they were so potent. This then opened a Pandora's box. Many groups added more gases. In fact, Dr. Henson's group had a paper a year after that pointing out other greenhouse gases. So now we sort of have a good idea all the pollutants that are warming the climate. There was one more issue to be sorted out. It was around the 1980s, models were suggesting there's this black carbon, soot, basically the black smoke you see from diesel and your cooking fires, and they were contributing to warming. They are not green, they are not gases, they are particles, they're not greenhouse pollutants, but they were absorbing sunlight directly. It's the most, per ton of this black carbon, it's the most potent trap of sunlight, so we wanted to quantify this. So Paul Crutzen and I, we proposed an experiment that we will go to the Indian Ocean. During the wintertime, you see massive amount of air carrying all the pollution by more than 1.5 billion, and it's transporting over the northern Indian Ocean. So we thought we'd take a simple ship, boat, put our instruments and go north and south, because once you're here, you're seeing air from Antarctic, clean air. So we thought it's a perfect experiment. But what started as one boat ended up in 6 aircraft. Over 20 nations joined this experiment, including India. And Europeans moved a satellite, so we have full coverage. So what we were shocked to see is this massive amount, river of pollution, okay? And we had aircraft measurements to really precisely pin down the chemical composition. I'm not going to go through all this, mainly let me focus on the black carbon. The black carbon was only about 10%, yet it was the most dominant effect on this radiative heating of the planet, and we wanted to measure this directly. How do you measure this? So in my lab, I designed small UAVs, wingtip to wingtip. It's about 3 meters. We squeezed about 14 to 15 instruments in this. The top UAV would measure how much sunlight was coming in, how much was going out, and the bottom would measure how much was transmitted. And this middle guy would go up and down to sample what exactly was there. Using that, we were able to pin down the solar heating by black carbon, okay? And then we also were able to show this black carbon over the Himalayas is part of the reason, but other groups had shown where the glaciers are melting. So finally, we know how we are warming the planet. Carbon dioxide, the surface area depicts how much heating, the thickness of the blanket. And these were the non-CO2 trace gas. I talked about CFCs. They were replaced by HFC, hydrofluorocarbons, nitrous oxide from fertilizer, ozone. We don't emit ozone, but we produce ozone by these pollutants. That's methane, and this is black carbon, okay? So now we know how much heat we have added and how we did that. So the next thing is, how does the system respond? So the planet begins to warm, and then it starts a chain of feedbacks. The most dominant one is the feedback due to water vapor. Sorry, I think, let me take a digression. So these pollutants, non-CO2, are called super pollutants because they're at least an order of magnitude more potent than CO2 per ton of these emissions. So there are 2 types. One is short-lived. Their lifetime is less than 15 years compared to a carbon dioxide molecule in centuries to millennia. And there are long-lived, which is nitrous oxide. When you add them all up and use the IPCC estimate, they contribute about 50% plus or minus 10 to the heating of the planet, okay? Keep that in track. It plays an important way into the solutions. So let's talk about the water vapor feedback, right? The first thing you heat the ocean, it starts evaporating more water vapor and makes the air humid. And we heard that from Dr. Henson too. So what governs that? This equation, by the way, pretty much can tell you the whole story about why storms are intensifying, why droughts are intensifying. It's not the only one, but it's a dominant equation. It says the vapor pressure, how much water in the air, increases exponentially with the temperature. So when you differentiate this, and I'm not going to go through the math, what it tells you, for each degree rise in temperature near the surface, water vapor will increase by 6%. And remember, water vapor is the most potent greenhouse gas. So I wanted to quantify this. So first we said, is really atmospheric water vapor behaving like that equation? So this is the microwave satellite data, monthly average. We were shocked to see how closely the water vapor distribution, mind you, this is taken all over the planet, follows this Clausius-Clapeyron law. Instead of 0.406, it's about 0.055. Okay? Now the question is the blanket thickening? So that is the satellite data for the radiation budget experiment. We calculated the thickness of the blanket from the satellite data, and you see clearly the dominant thickness of the blanket is in the tropics where the ocean is warm, and it almost decreases by a factor of 4 as you go to the pole. So every year, the whole planet warms and cools. In July, it's the hottest because the northern hemisphere dominates it. So we thought, is the greenhouse effect of the atmosphere increasing with temperature? I have never seen a data confirm something like this. You can see the slope. And the magnitude of that, the rate at which the blanket thickens with temperature, was within 5 to 10% of what models like Dr. Henson and others had published. Okay, and without this water vapor feedback, the warming would be half as small. Honestly, I don't think climate change would be that serious a problem yet. Okay, so this is a spectacular confirmation of, originally it was proposed by Svante Arrhenius in 1895. So that's one. Now let me go to the other feedback. We know as you warm the planet, the glaciers would melt. Ice in the ocean is melting. In fact, my wife and I took a cruise to Alaska to see the sea ice before they disappear. So we wanted to see, the theory was, right, this was proposed by Budiko, a Russian meteorologist, that you see how when the lack of snow, the surface is dark. The snow surface reflects about 50 to 80% of the sunlight back to space. That's what keeps the polar region, as the cooler it is. Once you expose that, you are talking about a quantum increase in sunlight absorption. Same thing in the ocean. So this was a thesis work of one of my students, as 4 years ago. So this was the sea ice distribution in 1979. And in 2002, most of the sea ice is blown away, about 40% in the September. And the satellite data showed the planet is getting darker because it's absorbing more sunlight. And this is, again, the Earth radiation budget experiment data. This is the albedo, that is, from the skies, satellite, you see how bright the Arctic is. It has gotten darker. It was deflecting 38% of the sunlight. Now it's reflecting only 32. Enormous amount of positive feedback. Okay? Here, the magnitude we got was about 2 times larger than what the models were predicting. So that is how the warming gets amplified, feedbacks. I'm just talking about 2. I want to move on to other things. So we clearly understand how we are heating the planet, and we clearly understand how the planet is responding to that heating. And while I'm just showing you my work, there's tremendous amount of work in the literature on this, okay? So now let's move on to, we think we are reasonably confident about the theory. So how do you test a scientific theory? You make a prediction with it. So I teamed up with a meteorologist in 1980. We did a statistical dynamical model to see when will we see the climate signal from the weather noise. And we concluded the warming has to appear, should be detectable before 2000. Otherwise, we know that theory is something flawed or we don't understand the heating. And here I'm showing the globally average surface temperature distribution. And you can see that this is from 1860s. In this unit, it's about minus 0.6, and the planet has steadily warmed. We published this paper in 1980 when the planet was still on the cooling or in a sort of a limbo, right? And it was in 2000 when IPCC concluded they are seeing a statistically significant warming. So you can ask a question, wait a minute, why do you have to wait till 2006, 2000? The planet is already warming. You can't say this warming for a single year. You have to average it. So you needed at least 10 years of data from 2000 to 1990 to say that the signal is much larger than the noise. Okay? So I want to move on to, hopefully I persuaded you, the science Dr. Henson discussed and I discussed. We are on sound basis. So using that, let's make a prediction. Remember, I said we already added 2 trillion tons. That's enough to take the planet to 1.5 degrees in 10 years. Some are now saying it could happen in 7 or 8 years for a particular reason. So the 1.5 degrees is almost baked in unless we find a magical way to suck that CO2 out of the air. Okay? There's no technique I know which is scalable. But the problem is that by the time you go to 2030, when that warming shows up, you would have added the 3rd trillion ton, which would take you to beyond 2 degrees by 2050. Okay? So I want to tell you, again, focusing on the health, what are the health experts saying? What would the 2-degree warming planet do? These are basically, I'm summarizing publications, none of them are mine. 1.5 billion exposed to deadly heat. They came with a clinical description of what deadly heat is. Okay? And 600 million would be exposed to vector-borne disease because these vectors like mosquitoes would travel to warmer climate northwards. And widespread droughts. And this is mainly a mass displacement and migration. I don't know how many of you know, every year due to weather extremes, about 20 million people are displaced. When they're within their country, national boundaries, it's called displacement. When they move outside, then it's called migration, okay? That is just a 50% probability. Because of our feedbacks and nonlinear amplification, there is a 5% probability it could shoot to 3 degrees by 2050. So now let's move on, all right? I wrapped the science part of it. I want to go to the solutions. There are 3 singular events which happened to me, which made me change from shift to the solutions part. First is, we discovered in the Indian Ocean experiment, when I say we, I'm talking on behalf of 200 scientists, that 1/3 of the black carbon was coming from cooking indoors with firewood. I could relate to that. That is exactly, almost identical to the kitchen of my grandmother. I have sat where that cat is, and she would feed me hot food. So I could relate to this cooking issue. And I thought, this is a solvable problem, right? I mean, just giving clean cooking. The second event is, I was admitted to the Pontifical Academy of Science by Pope Benedict. So, I mean, normally when you're elected to the Academy, they the Pope personally elects you. There's a chain he puts, you can see on my shoulder. And Pope John Paul II asked me, Indish. So I wanted to say, yes, I was Indian, but no, I'm an American. But that didn't get properly transferred in Polish. So he started asking me, about India, but somehow I realized this is a teaching moment for me, okay? And the third is, 4 years ago, our President Janet Napolitano, she is a remarkable person. She was the Homeland Security chief under Obama. She declared the whole 10 campuses would become carbon neutral in another 10 years. So she asked me to lead 50 faculty from all 10 campuses to come up with, think about solutions. So we released this report called 10 Solutions, okay? Remember, this team of 50 had physical scientists, social scientists, humanities, even experts in faith, but mainly technology. So we put the solutions under 6 clusters. One is the science pathway, okay? And so there are 4 ways, there are 4 levers we have to bring the climate change. The first lever, of course, has to be carbon neutrality. If we don't do that, we are just wasting our time with the other things, okay? And that will give you a degree and a half cooling in about 40 years. The second is energy efficiency, all right? There's still a long way to go in energy efficiency. And I tell you, between the two, the low-hanging fruit is we are throwing away 30 to 40% of the food every year. Western societies is 40%, developing 30%. That alone would give you several gigatons every year. Just stop throwing food away. So this is the super pollutants, I'll come to that. And this is atmospheric carbon extraction. So we have 4 levers. Because of the delay in actions, you don't deploy any one of these 4, there is no chance you have to keep the warming under 2, okay? And the second one, which rose to the top, is societal transformation. And that's where I started working on. I'm going to give you some example of that. Governance, right? When people say, I'm going to cut down emission, how do you ascertain it? You have monitoring, you have governance. And the second is market and regulation. These are economists from Berkeley who proposed this: cap and trade, carbon tax, carbon dividend, and simple market incentives. The next one is technology measures. This is what the deep decarbonization, carbon extraction, cutting the super pollutants. So I want to just now tell you my bias and my focus. I'm not thinking about 2100. I'm focused in the next 30 years because I'm thinking of the 3 billion people who had nothing to do with this. Their carbon footprint was just 5%. We know when you have extreme droughts and heat waves, they're going to get wiped out. So my focus is, can we do something to keep that warming at 1.5, at least next 30 years, okay? So this is pulling the carbon lever, and you see that it takes about, we started it around 2020, it takes about 30 years, 40 years before it starts kicking in, bending that curve. So that's the no action, business as usual. When you cut these super pollutants, because their lifetime, black carbon is 1 week, it's gone in a few weeks if you stop its emission. Methane is about 10 years. That curve starts bending right away. So you have a fighting chance, at least up to 2050, with the super pollutant lever, to keep it close to 1.5. But you see afterwards, it loses its steam, its CO2 kicks in. So think of it as a relay race. The starter is the super pollutants. So he carries the baton until 2040 and hands it over to the CO2. That doesn't mean you can wait till 2040 to do the CO2. You've got to start all of them right away. And then you see but this is a 50% probability. If you ask me to give 95% probability, this will be from here to here. So we have taken a gamble, all right? So, let me see. Yeah. Sorry, let me point out. What's the difference to the people living in 2050? I can safely say I'm not going to be around. So So what do you say? How many do you protect instead of shooting past 2 to keep it close to 1.5? This was again about 10 papers have focused on this. There's going to be, I think, a sensational report released next week on this topic. It turns out, between 2 to 1.5, you can exposure reduced by 1.7 billion people to extreme heat. And the heavy precipitation, they estimate, could be reduced by 1/3. That is, if the heavy precipitation of 2 degrees is this much, that could be reduced by 1/3. And same thing, droughts, more than 250 million people could be saved from exposure to drought. So there is a huge gain in keeping it at 1.5 degrees. So the super pollutant idea has gotten hold. Now there are 2 efforts, the Climate and Clean Air Coalition by United Nations Environment Program. There is a remarkable Swedish head of this, Helen Valdez. She has recruited 16 national partners and 17 non-state partners. They have developed 15 solutions, measures to cut down black carbon, to cut down methane. It's being implemented in places like Mexico, Nigeria. And California, our Governor Jerry Brown passed a law. It's by the Senator Laureate. And his respect for science and scientists so much. When we were I was sitting in the audience, and he suddenly called me, he said, "Ram, you introduce us." So I had the honor of introducing this bill, which will cut down in California black carbon by 80%. This is from diesel. It's such a simple solution. It's the diesel particulate filters. Okay? Of course, it costs. When I say simple, the technology is there. And then we're going to cut the methane emissions simply by taking the farm manure, right, and capturing the methane and burning it for fuel. And you release CO2, but the methane is 25 to 90 times more potent. And the HFCs, we're going to go to HFC free. But this is also passed by UN. So I want to go to now the societal transformation. Our 50 California document concluded, without societal transformation, you have less chance of solving the climate change problem. So the first one here is the cook stoves. I was so fortunate, after 2-3 years, my daughter Nitya, who's not here, she started an NGO. She's a wireless technologist. See, this is a 100-year-old problem. Harvard, Princeton, MIT, they've been trying to solve this. And it never worked, because we don't know if they were relying on survey. So Nitya put a sensor in each of the stove, and she persuaded her sister, Tara, who's here, to do this field experiment in the field to document over 5,000 stoves that were instrumented. We have a much better understanding why these women are not using these stoves, and then how to fix that problem. The second societal transformation you see, we want to educate 1 million climate warriors to fight the climate problem. We think that's the scale we need. When we say climate warriors, we are talking about undergraduate students and others, young people. So we have created this course, okay? And this is launched in 7 campuses in the UC system. And now we are negotiating with university in Omaha, Nebraska, Creighton University, and 2 universities in Texas. And Stockholm is partnering with UC to take it to Europe. And I'm excited to say the National Taiwan University is now taking it up. So we're going to have discussions between UC and National Taiwan University. What this course focuses on solutions. The first lecture, I give the depressing part of it about climate change. Then the solution experts take over. And how do we expect to go to 1 million people? There are 4 components. One is the course, and then we are creating a digital book on the solutions. And the third is we are creating an online version. What does that mean? A professor sitting at National Taiwan University can teach all the students in Taiwan, provided the universities give them credit for it, okay? And the fourth is we are partnering with Coursera to convert it into a MOOC course. The next is that many of us in the Pontifical Academy are pushing for an alliance between science, religion, and policy. This is the summit. I worked with the Academy on bringing all the mayors, and you can see our governor here. So this was a meeting we held in 2014, and it was titled Sustainable Humanity, Sustainable Nature, Our Responsibility. At the end of it, all the attendees, remember this Pontifical Academy has about 25 Nobel laureates in all areas, physics, chemistry, biology, and scientists from all disciplines. So this academy, we came to this conclusion, finding the ways to develop a sustainable relationship with our planet requires ultimately also a moral revolution. Jim Henson talked about the moral issue, handing our children a damaged planet. I'm also focused, that's intergenerational equity. I'm focusing also on the intragenerational equity. There are these 3 billion people who have still not discovered fossil fuels, but they are suffering the worst consequences of our fossil fuel consumption, okay? And I'm telling you, I started giving lectures in churches, and I see nothing but receptive audience. And I'm just not giving my lectures in the safe zone of San Diego, which is a liberal city. This is a lecture I gave in Omaha, Nebraska, invited by a Catholic institution. February, the temperature was 20 degrees outside. 750 people showed up. And many of them came from the rural areas, and their statement to me was, Professor Ram, we didn't know climate change had so much science in it. And because of all this, I'm sort of extremely happy to tell you the president of the American Evangelical Association, which oversees 30,000 churches, Reverend Leith Anderson, came to our meeting on climate change at the Vatican. Apparently the first time an evangelical leader has gone to a Catholic thing. Again, I don't want to mislead. I'm not thinking this is all going to solve the problem. Just to those of you, individual efforts could make a huge impact. Each one of us can do something about this. So finally, to implement all the 10 solutions, most academics in California have gotten together. So we have formed this coalition called California Collaborative for Climate Change Solutions. And we have institutions like Caltech, all 10 campuses of the UC, Berkeley, Irvine, Stanford, University of Southern California, 20 campuses of the state system. So what are we planning to do? Take the innovations at the bench level, do demonstration projects on the scale of about 50,000 population. We will take only those solutions which have a potential of at least taking out 1 gigaton of carbon, okay? And then find out which of these solutions would work, and then scale them up, bringing in commercial partners. We are already in discussion with a lot of industries, including the energy and oil industry. So, just the moral of the story is that the situation has come to such a state, we cannot just wait for top-down efforts. They are critical, don't get me wrong. But till the national leaders figure out the urgency of the issue, each one of us, we have to do what we can to keep that candle burning till the nations come to sensus on this issue. So my motto, I want to leave with you this, and it's basically, knowing is not enough, you must apply. Willing is not enough, you must do. I wish I had thought of it, but the German philosopher Goethe is the one who said it. Thank you.
Well, I think really had the privilege to hear two prominent scientists to show how they have applied their knowledge, their scientific findings to solve this particular problem, to fight the battle for achieving how to bending the curve. Let's thank Professor Henson and Ramanathan for their wonderful speeches. Thank you.
Thank you very much, Dr. Liu, for hosting this session for us. Thank you. And thank you again to our laureates, Dr. Henson and Dr. Ramanathan, for your inspiring lectures. Ladies and gentlemen, this is the end of the Sustainable Development Lecture. Thank you very much for your participation today. If you have any questions regarding the lectures, you're welcome to join the press conference on the first floor.